Welcome, ladies and gentlemen, to this section. We're going to be looking in detail at the definition of continuity, because continuity is a very, very important, critical part of calculus. And we're going to be really looking at this into detail and examining the definition and also looking at this theorem. So what I'm going to do right now, because it's going to be very vital that you have this information in front of you, I'm going to step back and I'm going to ask you to copy all of this information, because you're going to need this, because again, I'm going to take you by the hand, step by step. And also, I'd like to welcome my class. Welcome class. Jimmy, John, Ralph, Maria, Asia, Antoinette, Sue, Felicia, Tony. All right, there you go, Marilyn. Very good. Excellent. Give yourself a hand for joining our class today. Very good. And I hope that all of you are going to find this class very helpful, enlightening, and that is going to help bring to light some things that you really needed to see that just wasn't clear to me when I was learning this in high school. So right now I'm going to move out of your way, give you some time to copy the board, and then at one point, about 1 or 2 minutes later, I'm going to ask you to pause the video, copy this information, because I'm going to need to clean the board and then move on at particularly looking at this particular theorem. We need to look at this theorem of how that relates, because this is the definition of continuity. So, as promised, let me move out of your way. Please copy that information. Oh, I'm sorry. Let me go over this. This is the definition of continuity. And let me get my professor stick. I feel more relaxed when I got my power stick, my professor stick. All right. This is the definition of continuity. First of all, the function must be defined at that point. Some books call this point-wise continuity, because also later on in higher level math, we're going to need to look at uniform continuity to make sure that a function is continuous throughout an interval. This, in some other books, is known as point-wise continuity. F is defined at A. F of A is defined. So that function exists. The limit of f of x as x approaches A, that also exists. So the limit, and look at number 2, that is going to be critical when we begin to dissect and look at the definition of differentiability. That differentiability implies continuity. Number 2 is going to be extremely critical, because there are key words there that I'm going to highlight to help you get a better understanding if you didn't see it. Also, the limit of f of x as x approaches A, that has to equal f of A. So the limit must also approach f of A. Whatever the numerical value is, the limit must equal to the numerical value of f of A in order for that function to be continuous at A. Also, we're going to utilize this line segment. Here goes our first point, and we're just going to increase this by a small increment. Just pretend that this is a microscope and that you've enlarged it so you can see the increment. Actually, we're looking at something real small. And we're going to increase that by just delta x, a small space. When I add that amount on to A, that gives me my next value, x. So from this line is going to be very critical to understanding how I'm going to explain this theorem to you. So please copy this line. Also, A plus delta x, A plus a small increment gives you your x value. Using algebra, when I subtract A, therefore delta x also. Let me put this here. So this has a beginning. This is 0. There we go. So we have a beginning there. So we had the length of x and the length of A. When I subtract the length of A from x, that leaves me this space, that delta x. So delta x is equal to x minus A. So please make sure that you copy this down. Let me go through this theorem. The equality of these statements. We're going to be showing how all these statements are equal to each other utilizing that line segment. So please do not take this for granted. That line segment is going to be very essential into examining and proving the statements in this theorem. So let me go through this. The following statements are equivalent. 1. F of x is continuous at A. The limit of f of x as x approaches A is equal to f of A. The limit of f of A plus delta x as delta x approaches 0 is equal to f of A. Also, the limit of delta f as delta x approaches 0 is equal to 0. And delta f is defined to be f of A plus delta x minus f of A. So ladies and gentlemen, at this moment, please now copy this information. I'll give you 1 or 2 minutes, and then I'm going to ask you to pause the video if you haven't copied it within that time interval. Then we're going to move on. Let me move out of your way as promised. Please copy the information from the board. You will need this to follow along. So I urge you, please, copy this information, because we're going to look deeply into this definition and the theorem of continuity to give you a greater understanding so it does make sense to you. Please copy this. All right, ladies and gentlemen, at this time, I'm going to ask you, if you have not completed copying the information from the board, at this time, please pause the video and finish copying the information. Then when you've done that, then you may restart the video so we can continue on with the class. Joseph, John, Ralph, Maria, Elizabeth, everybody, please make sure you have this copied down, all right? Very good. Excellent. Okay, ladies and gentlemen, at this time I'm going to pause the video. I'm going to erase the board, and now we're going to examine the theorem, and we're going to show how these statements are all equivalent to each other, and then we're going to look at the definition of differentiability, how that implies continuity. We're going to use this information from the definition to really point out and make sure that you really understand, so that it's just not something that's esoteric or abstract to you. So at this time, I am going to pause the video so that way you may have an opportunity to complete copying the information from the board. I will see you momentarily. All right, ladies and gentlemen. Now, this is what we're going to do. I'm going to take it slowly. We're going to prove the equivalencies of these statements. Here's what we're going to show. We will show the following. Here's what we're going to show. That statement 1 is equivalent to statement 2. That statement 2 is equivalent to statement 3. And that statement 3 is equivalent to statement 4. This is going to be essential to examining the theorem on showing that if a function is differentiable at a point, it's continuous there. So what I'm going to do, please copy this down first. Then I'm going to move on. So what we're going to show that 1 is equivalent to 2. 2 is equivalent to 3, and that 3 is equivalent to 4. And we're going to be utilizing the geometry of that line segment in order to prove this as well. Okay, at this time, if you need more time, please pause the video. All right, let's take a look at showing that statements 1 and 2 are equivalent. Show. So first of all, statements one and 2 are equivalent. Why? So, class, Veronica, why do you think statements 1 and 2 are equivalent to each other? Let me step back, give you a moment to think that over. While I'm waiting for Veronica, I want you to think it through as well. Why are statements 1 and 2 equal to each other? I got to give her a little time. Got to give her some wait time to think it over. So look closely at statements 1 and 2. Why do you think statements 1 and 2 are equivalent to each other? So let me move out of your way, give you time to think that over. Oh, okay, Veronica, so you're ready. Okay, so what's your answer here? Very good observation, Veronica. All right, let me check with my other student, Veronica. Let me see if they have seen their similar observation. Okay, Veronica gave me her observation. It came crystal clear. She was able to finally see it. Do you know why statements 1 and 2 are equivalent to each other yet? What are you thinking? What do you see? Okay. All right, so you're still thinking over it and you're wondering. Okay. Thank you, Jose. I appreciate that. All right, so now what I'm going to do is I'm going to move on and let's look at this closely. Well, in this case, statements 1 and 2, that's simply the definition of continuity. So, in this case, let me write this down. Statements 1 and 2 are merely or simply the definition of continuity. So these two statements is just a restatement of the definition, or simply the definition of continuity. This is why statements one and 2 are equivalent. To one another. That is why they are equivalent to one another. They are simply restatements of the definition of continuity. Now you guys understand, Veronica, Paul? Very good. What about you? Carlito? Very good. Okay, Maria. All right, so you do understand that statements 1 and 2, they're simply the definitions of continuity. Okay, everyone see this? Do you follow that now? Okay, the limit of f of x as x approaches a is equal to f of a. This is saying that the limit has the same defining value as f of a. So by definition, it's continuous there. Also, when I increment this, as this little increment, this space gets smaller and smaller and smaller, the distances between that, and this is also another vital part of studies of mathematics called metric spaces, and this is the foundation of that. This is called a metric space. As the distances, is dealing with distances, as the distances get smaller and smaller, we're getting closer and closer to that letter or that number A. And eventually, if it is continuous, it's going to overlap. So therefore, the distance between those two is 0 because we are simply